This is the heat transfer project of Brendan Calloway and Bradley Johnson. We analyzed the subterranean heating of a greenhouse. In this picture here you can see the particular greenhouse we're studying on my mother-in-law's property. It's a 6 by 6 by 8 greenhouse. It's pretty small, and it's currently not being used because it gets too cold in the winter for it to be used, and so it's not being used at all. We're hoping that with this analysis we can find a way to keep the greenhouse running year-round. And so the purpose of this analysis is to determine if on the coldest day of the year and the coldest night of the year in Rexburg, Idaho, if we can keep that greenhouse above freezing. So first step was to look at the temperature of the soil at various depths in Rexburg, Idaho. So in this image on the left, you can see that the temperature of the soil is going to vary by some amount based on its depth from the mean annual ambient air temperature of whatever place you're in. So on the image on the right, you can see that in Rexburg, Idaho, the mean annual ambient air temperature is 42 degrees Fahrenheit, which is 11 degrees Celsius, 10 degrees Celsius. And so once you get down to about 30 feet below the surface of the earth, all of the soil temperature there will be 10 degrees Celsius. And as you get closer to the surface of the earth, that temperature will be closer to the ambient ambient air temperature. Golly. All right, so we ran some numbers trying to figure out how exactly this was going to work. And so in this hypothetical situation here, we have the coldest night of the year in Rexburg, Idaho, which last year, the coldest night of the year got down to negative 11 degrees Celsius, which is 12 degrees Fahrenheit. And so we use that, the difference between the 30-foot temperature, which is 10 degrees Celsius, and the negative 11 degrees of the night. So we have a delta T of 21. We have a U value of 0.66, which is the U value for double layer plastic, which is what the greenhouse is made of. We have a surface area of 260, which is based on the geometry of the greenhouse itself. And we come up with heat loss from the greenhouse due to radiation and convection of about 2.875 kilowatts. And so in order to maintain a constant temperature in the greenhouse, we need to bring in an equal amount of energy. So using internal force convection equations, Nusselt correlation, we determine that in order to bring in that 2.875 kilowatts of energy, and just with a couple of random numbers thrown in, 1 for velocity and 0.15 for diameter, we come up with a required length of piping of 56.7 meters. Now, 56.7 meters is a lot of meters, and so we wanted to optimize this so we can find what pipe diameter, what air velocity we could use in order to decrease the total length of pipe and actually make this a practical idea. So you can, from this graph, you can see we have at several different air velocities pipe length as a function of diameter. And so you can see that as the diameter increases, the necessary length of pipe decreases. And so in order to really decrease the length of pipe, we'll need a larger diameter pipe. We also did the same with velocity, and you can see that as the velocity increases, the necessary length of pipe decreases as well. So in order to get a really short length of pipe, or at least a short enough length of pipe that we can do this project without needing 50 or 60 meters of pipe, we just need a slightly higher airflow velocity and a slightly larger diameter. We ran through all the numbers, we optimized everything all together, and just with 0.3 meter diameter pipe, At 2 meters per second air velocity, we only require 19 meters of piping, assuming we get down to that 30-foot depth, which will have that air temperature of 42 degrees Fahrenheit. I guess the only thing that might not be plausible about this now is that it would be a lot more difficult to dig down to that 30-foot depth. And so if we were to use, like say we only dig down 10 feet, then we might need to double that pipe length or do something along those lines in order to maintain a sufficient air temperature in the greenhouse to keep all the plants alive. Now this is the way we have this set up now, it would keep the air temperature in the greenhouse equal to the air temperature at 30 feet and the mean annual ambient air temperature at Rexburg. So we could also dig a little shallower and just keep the greenhouse above freezing, and that way plants could live year-round even if they wouldn't be germinating year-round.